Usually the bonds are represented as lines between atoms in valence bond theory, which differs from the molecular orbital theory. According to valence bond theory, the bond formation is due to the overlap of the atomic orbitals, which makes bonds localized between the adjacent atoms. This differs from the molecular orbital assumption, where bonds are delocalized over several atoms. Notice this bond representation causes a problem when used for the formation of covalent bonds of the second period. For example, as we saw in this figure, the two p orbitals are at the right angle to each other. So if, for example, atoms such as carbon forms four bonds, it will use the 2s and 2p orbitals, and we expect the angles of the covalent bonds to be 90 degrees. And instead, we find angles of molecule with single bonds only, such as methane, approximately 109.5 degrees, and 120 with molecules with double bonds, such as ethylene, and 180 degrees with molecules with triple bonds, such as acetylene. To overcome this problem, Linus Pauling proposed that atomic orbitals combine to form hybridized atomic orbitals. These hybridized orbitals overlap with the other atom's orbitals to form the observed covalent bonds. So what do we mean by hybridization? Hybridization is a mix of atomic orbitals to form new hybridized atomic orbitals. The combination of atomic orbitals and the formation of new hybridized orbitals influence the molecular geometry and the bonding properties of the molecule. For example, the hybridization of the s and p atomic orbitals results in the formation of either sp3, sp2, or sp hybridized orbitals. Notice the combination of the wave functions of 2s psi and the 3-2p wave functions psi2px, psi2py, and psi2pz gives us the same number of hybridized atomic orbitals sp3, sp2, or sp, where each can contain up to 2 electrons. The superscript numbers 3, 2, and 1 tell you how many orbitals are hybridized. For example, the sp3 means one s orbital is hybridized with 3p orbitals, where the sp2 means one s orbital is hybridized with 2p orbitals, and the sp means the s and only one p orbital are hybridized. Let's look at the formation of each type of the 3 hybridized orbitals. The first type of hybridization is between the s orbital and the 3p orbitals, which results in the formation of 4 equivalent hybridized orbitals, sp3 orbitals. The 4 sp3 hybridized orbitals each consists of a large loop pointing in one direction and a smaller loop pointing to the opposite direction. The axes of the 4 sp3 hybridized orbitals point out from a regular tetrahedron shape. Notice, because sp3 hybridized orbitals form due to the hybridization of one s orbital and 3p orbitals, the resulted hybridized orbitals have 25% s character and 75% p character. To understand the sp3 hybridization, let us look at the methane molecule. We used the VS-EPR theory to predict the molecular shape, and we know that it forms a tetrahedral structure with equivalent 109.5 angles between bonds. The carbon atom has 4 valence electrons, 2 electrons in 2s and 2 in the 2p orbitals. The hybridization between the 2s and 2p orbitals results in the formation of 4 equivalent in energy sp3 hybridized orbitals. Each has 1 electron. The 4 hybridized orbitals overlap with 4 1s orbitals from 4 hydrogen atoms. Each contain 1 electron to form the 4 CH bonds. Here is the overlap of the 4 sp3 orbitals of the carbon atom with the 4 1s orbitals of the 4 hydrogen atoms, which results in the formation of the 4 sigma bonds. The 4 CH sigma bonds have equivalent 109.5 angles in between. Other examples of the sp3 hybridization is ammonia molecule. The nitrogen atom also undergoes the sp3 hybridization to sp orbital hybridized with the 3-2p orbitals to form the 4 sp3 orbitals, with one lone pair of electrons in one of the sp3 orbitals, and the other three sp3 orbitals each has one electron overlap with the three 1s orbitals of the three hydrogen atoms. Another example for the sp3 hybridization, the oxygen in water molecule, which undergoes also the sp3 hybridization. The 2s and 2p hybridization give 4 sp3 hybridized orbitals. 2 of the sp3 are filled with the 2 lone pairs of oxygen, and the other 2 sp3 orbitals each has 1 electron, for the total of the 6 valence electrons. The 2 sp3 orbitals overlap with the 1s orbitals of the 2 hydrogen atoms, forming the 2 OH bonds.